The broadcast is now starting. All attendees are in listen-only mode.
Thank you for attending RSA webinar today. My name is Artur Kosakowski and I will be running today's presentation along with my colleague Rafał Gawenda. The topics of this webinar is steel design, how to build a model and assign design parameters. You can find information about our new series of robot webinars under these links. Let me remind you about the concept of the RSA webinars. We will focus on one or several topics in order to discuss issues frequently submitted to the support team. We'll begin with the general introduction of the selected features of the program and develop these subjects further based on the feedback we'll receive from you after each of the presentations. Please mind that these webinars are not supposed to be training sessions. In this webinar, we'll cover the way to create a model which matches the requirements of the steel design module of robot. We'll get you familiar with the definition of loads and load combinations, and finally discuss the definition of parameters which govern code checking of steel elements of a structure. Again, please mind that this webinar is not a step-by-step guideline, but is intended to illustrate the principles of defining the right steel structure model and to explain the rules which govern the code checking of elements according to the selected steel design code. For the next webinar, we'll focus on the RC design module of robot. Regardless of the kind of a structure you design, it is extremely important that you create its model in a manner that allows you to assign correct design parameters to each of its elements. My suggestion is to define elements of a model in such a way that enables you easy definition of SLL limits for each of them. I'd like to focus your attention on the fact that in order to be able to assign correct deflections limits to multi-span beams, they should be defined with separate elements for each of the spans. In addition, cantilever should be entered as separate bars too. Let's try to do so for selected beams from a sample model that I prepared. Okay, let me select the group of beams, and if you have a look, I define these beams being from column to column, from the support points to the support points for monorails, and cantilevers being a separate elements. So okay, let me exclude cantilevers for a moment from the selection because we'll focus on them later on. But for such selection, I can create a new design group okay, and we may name this group SLS beams, for example, and when we go to the service button, we can mark the correct deflections limits. And now we can assign these parameters to the beams of the model. For the columns, I recommend to enter them as single elements between levels instead of being defined through the entire height of a structure. This also allows for easy definition of the horizontal displacement limits. This is also recommended for models with defined seismic analysis, especially when you want to access results for stories. So if I go back to my model, then I can select group of columns, and as you can see, they are defined from the bottom, from the foundational level to the main beam level, and also from the deck level to the silo. And if I define a new set of parameters, SL columns, for example, then I have to make sure that deflection limit or displacement limit is marked like this rather than as for beams. So again, I can save this set of parameters and assign them to the elements of the model. In case a beam or a column is built from a chain of smaller elements, you should define, as we named it, superbars. This is also valid when you divide it, a beam or a column into smaller parts to create connection, or when there is a change in the section along a beam or a column. Again, let me go back to my model, and as you can see, I created superbars for the main columns of my model, and you can clearly see that this is the component, these are the components, and this is the entire superbar that is created based on the list of smaller elements. For design of columns, you may also want to include additional bending caused by the fact that the shear connection with a simply supported beam is actually located at the face of the column rather at its axis. This can be done automatically by defining relative shortening in the offset definition dialog. So let me move back to my model to illustrate how this could be done. Okay, so we have another group. We have a main beams defined between the columns, and if I go to the offset option, I defined this relative shortening, reduced length, and if I apply that to these beams, you can see that the beams are actually shortened. Right, so the force will be applied at the face of the column. To illustrate that a bit better, let me change the cross-section of the columns. So I will select the columns and I will replace that with a large section, and you can see that the beams are automatically shortened corresponding to the increase of the size of the column. To define partial releases, which represent real stiffness of connections, you may use elastic releases, and the value of this elasticity can be taken directly from the steel connection module, or sometimes you may just use the partial stiffness coefficient instead, and this also allows you to deal with the model with large number of releases to avoid instability during the calculations. It is recommended to define a point load along a bar with additional generation of a calculation node. By doing so, you make sure that the steel design module will automatically carry out the verification at the location of such defined concentrated force. The reason is that the verification is done in a specified number of points along each of calculation elements, which are generated between both user-defined nodes and calculation nodes. So to illustrate, let me go back to my model. I will create a new load case. Okay, let's give it a number 100. And then I will apply new load, bar load, point load in the middle of, for example, monorail 14. Okay, so we have force defined, and now I will run the generation of the calculation model of my structure. This is to generate these calculation elements so that you can see what is the influence of the calculation node defined along the element. Okay, so let's open this selection in a new window, and now if we go to the attributes dialog, we select nodes and numbers of calculation nodes, the same for bars. Okay, you can see I will increase the numbers. You can see that we have two elements, so the verification will be done at this point. Okay. In robots, there is no automatic pattern loading generation, therefore you need to define live loads for each of the spans of the continuous beams as separate load cases. Then you can use automatic generation of code or manual combinations to have all possible load schemes. Mind that for multi-story buildings, you may want to group live loads to avoid excessive number of automatic or manual combinations. Let me show how to generate automatic code and manual combinations. Mind that you should have correct types of combinations in order to be able to run check for ultimate limit states, serviceability limit states, and fire provisions respectively. So, okay, I will go back to my model. I will reload it so that I have the option for defining the loads and load combinations. Okay, so let me go to the automatic combinations dialog, and now you can see that we have option for generation of automatic combinations according to the selected rules, the selected codes. Estimated number of combinations is 390. You can select which loads are taken into account, which kind of combinations you want to create, and you may define the different relations between the group. We press the generate button. For code combinations, we need to calculate the model to see them being generated, and we can go to loads and combination table, and we have all of them created. There are a group of filters. You can filter the display for ultimate limit state, serviceability limit state, accidental or fire combinations. You can also go to the same option and this time select automatic generation of manual combinations. The rules are exactly the same rules as for code combinations. So when you press the next button, you may have manual combinations generated in an automatic. If we go to the load, to the combination table, now you can see that you have all the manual combinations generated. Mind that if you both of them in your file, when you switch to code combinations, you need to select the display of code combination components. When you want to see combinations, you need to select combination definitions. The code checking of steel elements of a model is done based on parameters assigned to each of them. In the program, there are some predefined member type labels, but you may consider creating your own types, for example, the one for typical beams. Mind to set both ultimate limit states and serviceability limit states parameters. For typical beams, you may consider using automatic detection of elements which prevent the beam from buckling in each of its two local planes. You may also assume that in most of the situations, load is applied to the upper flange of a beam and adjoining elements stand for restraints against lateral buckling for this flange. For the lower flange, as lateral buckling can happen only when the flange is under compression, you may set the restraints at the locations where bending moment changes its sign. Let me show this on another example. So let me load another file. Okay, that's going to be example of a platform. Okay, let me adjust the display and okay. Let me select all the typical beams of this platform, and then I will assign the typical beam label that I mentioned to them. Do we have it? Yeah, typical beams. And now, if I focus on beam 59, and okay, let me go to the steel design module, select the element 59, and then go to its parameters, you may see that there are no restraints for buckling Y because there is no restraint in the vertical direction. There are two beams in the horizontal direction, which is correct. That's buckling Z restraint. Lateral buckling for the upper flange. Again, we have these two secondary beams. And for buckling for the lower flange, we have one restraint at the beginning and one, let's say, in 1/4 of the element length, which is supposed to correspond to the bending moments from self-weight. So if I display bending moment diagram and we look at this beam, you can actually see that this is true. This is the position when the bottom flange starts to be in the compression. If we look at another beam, for example, beam 14, this is the same situation for buckling, no buckling in the vertical direction, two restraints in the horizontal direction, which is correct, two lateral buckling restraints, and for upper flange, and there is no restraint for the lower flange, because if we have a look, or there are some at the ends of the beam, because if we have a look at this beam, we can see that it actually has got releases defined at the ends, so there is no bending, there is no compression in the bottom flange of the beam. For columns in irregular buildings, you may use automatic buckling length option, which calculates buckling length coefficients for a column based on the stiffness of elements which are defined in its top and bottom nodes. Again, let me remind that SLS limits for columns should be set in a different way than for beams. For columns in irregular structures, as well as for trusses or electricity towers, you may refer to values suggested in the literature and enter the recommended values of buckling length coefficients in the way shown on the currently displayed slide. Mind that in addition to setting the correct values of unrestrained buckling and lateral buckling lengths for cantilevers, you should also mark the corresponding checkbox in its SLS parameters. This will influence the way program checks the value of deflection, which I'll explain in a more detailed way just in a second. SLS for beams is checked based on the maximal distance from line which connects the start and end nodes of a beam on the form structure to the line that represents the form shape of a beam itself. For a cantilever, this is done based on the difference in positions of the origin and end nodes on the deformed structure in the directions which corresponds to the local axis of the cantilever. The check for a column is done in the similar way as for cantilevers, but this time in the directions of the X and Y axis of the global coordinate system. Let me show the difference in obtained values for the cantilever option switched on and off for two selected bars from my sample model. Okay, I will load the model with two silos, and if you look at the deck, there are going to be two small lifts defined there, which have nice looking cantilevers, which I use for the illustration of the part that I just covered. And if we look at them, if we look at element 521 and the parameters, you can see that for deflection, I haven't checked the cantilever option, whereas for the other bar, which is 860, you can see that this checkbox is marked. Okay, so let's run the verification of these two elements. You can see the difference in ratio. For beam, the value of deflection is going to be 5 centimeters, whereas for cantilever it is like 40 centimeters. And if I now select the nodes that belong to these bars, and if we check the value of the displacement of these nodes, okay, you can see that the 40 is actually correct and the deflection calculated without the checkbox marked for cantilever is entirely wrong. So you have to be careful to mark this option if you're designing cantilevers. Please remember that you can save the definitions of member types in your user setting folder using the label manager dialog. This allows you to use them in other projects as well. The verification of a section capacity is done in the declared number of divisions along each of a calculation element generated along a bar. As I already mentioned, the calculation point defined along such bar splits it into two calculation elements, meaning that the check will be done on both the left and the right side of the calculation node. This is why I suggested to define a point load with the generation of a calculation node so that this point is not skipped during the code checking of a bar. In addition to the division points, you may also include points where the absolute values of internal forces are the highest. In some situations, you may want to disregard secondary effects caused by very small internal forces and, for example, run the design for pure bending, with axial force being excluded, or tension compression plus unidirectional bending, no bending in the weak direction then. This can be done in the dialog shown on the currently displayed slide. Mind that when you want to disregard both positive and negative forces, for example small tension and small compression, you need to enter both positive and negative values. It is recommended to use the relative limits being the percentage of the admissible stress rather than set absolute values, as such setting can be used for all sections regardless of their sizes. In order to find the best matching sections, you need to create design groups. Usually they contain several elements of a model for which you want to have the same section. Therefore, in a situation when you want to design each of elements separately, you need to create design group for each of them. This can be done automatically by typing all divided by one string in the member list and then pressing the Save button. Mind to select the correct material for each of the groups, which usually is the same as the material defined for bars that belong to this group. In case you want to compare what the strongest steel grade influence on the section size is, you should create a new group with this type of steel for the same list of bars as used for the original group. Mind to check that all bars from the list have got the same steel grade so that you don't change it when you replace the initially assumed sections with the one found during the code checking. By default, the search for best matching profile is done within the family the initially assumed profile is taken from, but you can run design for more than one family at the same time or just few sections that you actually have available. By default, the selection is done based on the design ratio, but you can decide on the weight criteria instead, as well as impose restriction on section dimensions. You can find the bars or groups which failed the verification by sorting them by their design ratio. I'll show this in a moment on my sample model of steel structure, which I also would like to use for showing the steel design process in robot. Let me switch to the program and open the model. Okay. So let me start with displaying the sections that I originally assumed for the model. We'll show that in colors. Okay. And then I will run the verification of all these elements to see how far my initial assumption is from the optimal design. I can quickly check that by selection via map. So this is the sections that failed. I can open them in a new window and we can see the design ratio. And this is the sections that are severely under-designed. So something that I should probably find smaller sections for. Okay. So as I mentioned, the design is based on the groups. So I created several design groups. And you can make the selection by design group. For example, group 1 stands for the main columns of the model. And then to find the best sections, I will run the code group design for all the groups, and I select the lightest section as the target. First, I will design them for ULS, for the strength limits. Okay, check design is done. So we can see the section that is found as the best matching and the lightest. So I will replace the original section in the model with the one proposed by the program. You can see the change in the colors of the elements of the model. When it is done, yep, you can see it might have smaller columns. Now the status of the result is out of date. I need to recalculate the model to have the correct value of internal forces as the stiffness of elements changed. Okay, so that's going to take a moment. There's quite a number of load cases defined in this tiny model, apparently, but it's not that tiny, to be honest. Good. So we have the model calculated. So now I need to check whether newly found sections are correct. So I'm running the code group verification. As I change the sections that influence the set of forces, so initially sections for a different set of forces may be wrong, and usually this is true. Let me sort by ratio. It's okay, we have like the three groups that we need to focus on. So what I'm going to do, I'm going to design these three groups, not all, but the one that failed, which is 12, and then 69, and last is 42. Okay, so let's run the check for the best sections for the new set of forces. Okay, and let's change them again. Okay, so I need to recalculate the model again. The still design is sort of iterative process, so you make the assumption, you optimize the sections, you replace the sections in the model, then you calculate the model and check if these new sections are correct, and gradually you just narrow the search for the best sections to the smaller number of elements, and finally all of them are correct. Okay. So initially I have quite a number of groups to design. This time I designed only 3. And what I'm going to do now, instead of running the check for the groups, I'm going to run the check for all individual members of the model. And this time I will focus on each of them separately because the main changes for the groups are already done. So let's see how it looks like element by element. So we have only 2 elements that failed. So what I'm going to do, as I mentioned, the design cannot be done for a single element. I need to create the groups. I'm going to actually create a new group, and I'm going to type the list of the elements, in my case 2 elements, 1, 3, 5, 8, 7, 4, 7, and then divided by -1, and when I press the Save button, you can see that I actually created 2 groups. Okay, each of them have the element that needs to be redesigned, and the only thing is to check what kind of the sections we want to run the search within. Okay, by default I'm going to use the sections that are from the same family, and this time code group design is going to be for groups 73 and 74. So I narrowed my search now to 2 elements. Okay, and that's going to be the same story. I can change the sections and rerun the calculations. That I'm not going to do because it is exactly the same procedure, but instead I'm going to check the sections that I know are correct from the strength point of view. I'm going to check them for deflections or displacement. Okay, let's sort that by ratio. Okay, there's a couple of elements that needs attention. I can copy this list to the selection field to identify which elements I should look at. Now I will switch the display of the colors of the bars because they make the selection to be hard to recognize. And you can see that these cantilever platforms, which probably should be rethinking whether they should be defined like that. Maybe there's some other options for them. I've got a couple of beams, secondary beams, that I could increase. And it is the same situation as for a ULS design. You just run the group designed for SLS and the section find, and the program will find a larger beam. But sometimes there may be the situation that you simply cannot increase the size of the beam because of the restrictions, geometrical restrictions of the model, and in this case you may just consider another option, like for example having 2 parallel beams instead of a single one. So let me check what is the size of this section. Object properties. Okay, so this is 260 wide I-beam. So maybe just move it, copy it by the same distance, and then have 2 parallel beams instead. Yep. So if you cannot increase the section, you may consider just changing the geometry of the model or think about some alternative solution. Okay, so let me go back to my presentation. And now I would like to indicate, based on our experience, the most common examples of setting wrong parameters for design of steel elements. And typical errors include no member types assigned to bars, which results in having the empty list in the definitions dialog, lack of definition of SLS limits or leaving them as being inactive, defining components of superbars in the opposite directions. And finally, I would like to finish my presentation with a couple of useful tips. The exclamation mark in the results dialog indicates that the slenderness of the element is larger than the specified limit, meaning that the section should be increased. You can run verification in the selected location along a bar using the additional verification point, and then might to disable all other verification points. By default, the software displays the verification ratio from the point where this value is the largest. If there are several points of the same ratio, the first one is displayed. And this is very important. Do not change element length trying to define backlink parameters, as this may result in unexpected results of code checking. This part of the dialog is only available for compatibility with older versions of Robot, in which there was no option for definition of internal bracings that we covered during the typical beams label definition. To define backlink parameters, you should use backlink length coefficients instead. Again, mind that in Robot there are two families of angles, and one of them is defined with the properties in axis parallel to the legs, and this should only be used when direction of backlink is forced to be in the same direction as boundary conditions defined for particular element of a model, and there is no compression. Otherwise, use the family defined in the principal axis, especially when there is compression. To check the check of section capacity is done in its characteristic points. For pipes, you may want to first combine bending MY and MZ to avoid over-designing such elements. For user-defined sections, you should select the appropriate section symbol while saving it to the user section database. This determines the verification path, design formulas, and in addition, you should fill in the corresponding dimensions fields, which is important to correctly establish the section class. Mind that selecting the appropriate section symbols determines also the positions of sections' characteristic points. And seeing the opportunity, I'd like to introduce you to Autodesk Knowledge Network site. You can find a lot of useful articles there, and including the topics that we covered during this presentation. There's a couple of more links. And finally, I would like to ask you to ask questions using GoToMeeting questions tab. And again, I do apologize if we will not be able to answer all of them during the webinar, and in such case, please post them on the Robot forum after the presentation.
Thank you, Arthur, for very detailed about this steel design topic. And now we have time for question and answer session. Please post your questions in the questions panel on GoToWebinar window. So we are waiting for your questions regarding this topic. So far we have just only one question related to recording and publishing recorded webinars, and as usual in a few days the last recording of this webinar will be published as usual on our YouTube channel. Feel free to ask any other questions regarding steel design topic. So we can see some questions. So the first question I can answer right now is about the Service Pack 4. No, there is no Service Pack 4 for version 2015. It's already released Service Pack 5. It includes all previous Service Packs. So please download and install Service Pack 5 for version 2015. Another questions. Arthur, can you please repeat the point about typical errors? There was something with superbar defined wrong or something like that.
Yep, absolutely. Let me go back to the right slide. Okay, yeah. Right. So as you can see, if you have a components that have the local x-axis pointing in the opposite directions, that will be reported as the error during the verification. And you should just change the orientation on one of these bars. And there's another tip that you may find useful: the origin and end of the superbar. For example, when you want to assign intermediate bracing is based on the numbers of the origin and end nodes. The beginning will be in the node which has a lower number, the end will be in at the side where node has a higher number. So if you want to reverse that, because it is easier for you, you should renumber the end nodes of a superbar.
Could you please repeat the way of defining superbars?
Yeah. Okay. So let me maybe go to robot. So okay. So for example, okay. I have the column that is defined as a chain of two smaller bars, but I would like to assign the parameters for the entire height of the column, because I mean my deflection limit, for example, is the difference in the displacement between the top and bottom node. So in the on the members type, I just press the new button. Okay, that will create a new superbar. You may, for example, to distinguish superbars easily from the rest of the model, you may type the number that is significantly higher than the number of elements in the model. Then in the bar list, you should enter the numbers of the bars that stands for the beam or column. So it is 20 and 21. And you may, for example, name it like left column under a silo. And then you select the parameters, or you define the new set of parameters to this column. And that's all. And now if you just want to select your superbar, you type its number and it's already there. Yep, you can see the superbar and you can see the number of elements that are this superbar is created from.
There are some more questions about the superbars. So if we are in this area, so maybe it's time to dig a little bit deeper. Does the automatic backlink length in properties of superbar also works?
Automatic backlink length?
Backlink length for superbars.
Yes, yes. Yes, I mean that's based on the number of the element, yeah.
And
but let me again indicate that this is to be used only for regular structure, because if you use it for irregular structures, then the detection of the elements, top and bottom node, may not be done correctly.
And the question about adjoining bars parameters for superbars.
Yes.
Will there work for superbars also?
Yeah, I mean, in general, if you go to the parameters and you select this option here, you may indicate the number of the bar or superbar. So I think that, as always, for any option that you try for the first time, try to make a sample model and type the numbers of the joining bars being the number of the superbars. For example, a chain of beams or elements that stands for a beam, and compare the value of the buckling coefficient for the element that you want to check with the results you have got for automatic buckling calculations. This is the design, so you absolutely should check how the certain option works before going to the final design. This is probably the obvious statement, but I always check things on the small example before going to the large structure. It is simply to understand how the option works, or if the assumption that you make about how this option works is correct. So basic, yes?
About adjoining members, can this detection be made somehow automatically?
Yes. Okay, maybe that wasn't clear enough, I'm sorry. So if you select this option here, it is the same as using one of these options, okay, and indicate the elements manually. This is what is done automatically. So let me maybe go back to my PowerPoint. I believe that if I go back to one of the slides, there was quite a nice picture of that. You can see, okay, so this is the automatic detection of the buckling of the adjoining elements for this column, this middle column here. Okay, so this is the option, and okay, this is how it works. The element above that is detected in the same way as if you enter its number in this field, and so on. So this option will detect this element, this element, this element, and okay, in this corresponding to these positions here. So that's why what I said. I mean, you may just make a small model and then compare. You can compare the automatic detection of buckling elements, automatically calculated buckling coefficient, with the one that you obtain indicating the adjoining elements manually.
So one more about the superbar. Is code verification for superbars the same as for the members of the superbar?
Yes, absolutely. It is as you probably noticed, the set of design parameters refers to the length of the element. So in the situation when you have a beam which is defined, for example, as a single element, or another identical beam which is divided as three smaller elements, you create a superbar to be able to assign the design parameters correctly. So for example, if your buckling length is equal to the length of the element, it's rather hard to do so for 1/3 of the bar, right? This is exactly what I indicated in the tips, that you should not, where is it? Let me see. Okay, this one. This is actually that you should not play with member element length to define buckling parameters. So if your beam is divided into three elements, you should not type that okay, the buckling length of the element in the middle is 3 times larger than its length. you should create a super bar and define the backing element equal to the length of the bar. Okay. So, yeah, have I managed to answer the question?
Think so. So once again, about superbars, the question about creating the superbars with two perpendicular adjoining bars. How should the primary bar can be defined?
I'm not sure I understand. Like super bar with. Okay. Can you read this question again, please, Rafał?
Can you please repeat the part of the superbar with the two perpendicular adjoining bars? I'm not sure what's related to. How should the primary bar can be defined?
There is nothing like a two perpendicular or two parallel. I mean, the superbar is like the definition of the elements that are most of the cases collinear unless there is the curved beam considered. Actually, I'm not sure what is the superbar that is built from the perpendicular elements, if I understood the question correctly. Maybe the way to deal with that is if you could attach the screen capture or picture or a file on the robot forum, and then we will be able to understand this better and give you the better answer, because at the moment I can't think of the situation like that.
So next question, how to find the bar which and the group to which such bar belongs to if you have a large number of groups created?
Okay. If you look at the element in this dialog, if this element is defined in the group, you can see the number of the group in this field, and also you can see that in the table. Okay, there are code groups and there are components. And if we have a member, okay, then you have also the information about the element and the group it belongs to, for example. Yep. So either identification element group or group and list of elements.
So one question not exactly related to our topic, but it's you are kindly asked to create at least one still connection, and how to proceed with the still connections.
Okay. Because I've got results out of date, so let me reload this model. The design of the connection, or the definition of the connection, is based. Still connection is based on the selection. So, for example, if I select a column and a support, and then I go to the connections module, I can press this icon to create a connection. Okay, so we have the detection of the column because I selected the columns, and I have the detection of the connection type because of the support type. In this case, it is a pinned support because there's a pinned column-based connection because it is a pinned connection. A pinned support defined at the bottom of the column. So the same situation, I will select beam and column, and I press that button which creates connection. Again, there is the detection of the section size, and the type of the connection is based on the connection. Here we have shear plate connection because the beam has got the release defined at the end. And then the verification is done based on the load from combinations or simple load cases from the model. You can select the load cases. So for example, like the combination 77, and then we can just 77, we can run the calculations and check if the correction is correct or not. Yeah, in this case not. Of course, because I have very tiny angle, but you can go to the definition of the connections and you may change the size. Okay.
Question about the automatic buckling lengths. What's a regular and irregular structure type regarding what you have said about the automatic buckling lengths?
Okay.
What are the boundaries to classify the structure as regular or not?
First of all, the adjoining elements should be defined in the planes, in the local planes of the designed column. So if you have the beams that is like in 45 degrees comparing to the directions of web or flanges of this I column, that's not going to work. The same situation if the beam is not horizontal but inclined. Or there is a situation when you have like a truss instead of a beam adjoining one of these nodes. So basically, irregular is something like the example on the picture, typical warehouse or parking building, this sort of structure. Definitely not the one with the silo that I use for demonstration.
So there is a question about referencing or translating European standards to American ones. For example, comparable steel shapes and terminology in both standards.
Well, I'm not sure I understand the intention of this question. And basically, the steel design in each code is, I believe, quite similar. And the names for like buckling or lateral buckling should be the same as well. I'm honestly, I'm familiar with the terms that we use here in Europe, but I believe in the US there is similar situation. But if we go back to the steel aluminum dialogue, and if we now change the design code from European to American, yeah, okay, this is okay, this one is a current. Okay, there is the, if you change the code, the program tries to match the definitions done for the original code with the parameters of the newly selected ones. And then if we go to the parameters, the dialog looks pretty much similar in robot. You have a buckling, you have lateral buckling. There are some parameters that are typical for the particular code, but I don't know whether that's the answer to the question. I may not be familiar with. The one thing about the difference for European and American code is that for robot, in an American code, you may run the direct analysis method, which is like dealing with the buckling length of the columns, where you just apply additional horizontal force, and then reduce the stiffness of the elements, and run secondary analysis, both large p delta and small p delta, and in this way, instead of just trying to figure out what the buckling coefficient is, you assume it as equal to B1. This is I think similar approach to European imperfections. So even for Eurocode, you may run this direct analysis method to compare the results. For traditional setting the buckling coefficients with the approach with the second order analysis on the structure that is not vertical and has all the buckling lengths set as equal to the lengths of the columns. So I think that we are running short of time for the slot got for today's demonstration. So again, thank you very much for attending the webinar, and as I said, if there are still some questions that we were not able to answer, I would like to ask you to post them on the robot forum, and I would like to invite you for our next presentation, which is going to be for RC design module of robot.
One small addition, the recording of this webinar will be available within a few days on our YouTube channel. Once again, thank you for attending our webinar.
Yeah, thank you.